All right, great. So, all right, we discussed about Spark. All right, we said okay, Spark is really great parallel processing framework or engine to be able to work with these two wings, basically. These are main ones, volume and velocity. Okay, how does it work? In a Spark, we have two data structures. One of them we call data frame, right? Or let's say we call DF, and we have one more we call RDB. It's somehow different. It's not related to us because machine learning we usually need tabular data, right? If you need tabular data like this, right, we have to work with data frames, DF, data structure. Why? Because DF is like tables, like in Excel, like if you work with Python, in pandas library, right? Is a tabular data. So whenever we have tabular data, we have to work with data frames. Whenever you have non-tabular data, you need to work with RDB, another data structure. There is a big difference. If you work with tabular data, Spark reads data on a column basis, right? It means it reads data on the column basis, not row basis. Okay, because when we have tabular data, it means we have a schema, it means we have attributes. For us, attribute is important. Whenever you want to work with like ID or age, you need to get access to the column data, right? Or the column name. That's the reason we need to use data frame for interactive. Because data frame is designed for that, it's designed to be able to go through data frame quickly, optimize the optimized data structures for that purpose. But if you have data that you want to go through row, not the column, whenever I say row, it means there is no attribute, right? There is no schema. It's like a log file. The log file is the best example of unstructured data that there is no attribute, and the only chance to go through data is row-based. It means line by line. All right, so if you have this type of data, we have to go through RDB. But for main job, in this class is data frame. So let's say we have this data frame, and then first task, we need to partition data, right? Before doing any job, anything, you need to do partitioning. Reason we said that we have huge data, we need to run them in parallel. If you want to run them in parallel, we need to partition data. There are two syntaxes, guys. From now on, we have to work with syntaxes. So I'm not going to teach Python. I'm not going to teach SQL. I'm just going to tell you and teach you how to use Spark API, right? To be able to work with this machine learning and this parallel processing. All right. That's a really very high level programming language. We're going to go through it. PySpark, right? Python and Spark. Great. We have two syntaxes, repartition and coalesce. If you want to increase the number of partitions, let's say you have data, 10 gig, 5 gig, 1 terabyte, we need to decide firstly how many partitions. This is the first question. Okay, how many partitions we have to get over 3, 5, 10, 100, 200. But last week, I said something about the default size of data. Do you remember what is the base of data size for partitioning? Loaded, please. Sorry? 128, perfect. 128 megabyte, right, is the, let's consider it as the best size of data for partitioning, because CPU and memory, they are able to handle your data, mean 128 megabyte data quickly, right? Without any failure, right? 128 megabyte. In few cases, if you have powerful machine, let's say you have a machine with 19 cores, you have a machine with like more than 128 gigabyte memory. If you have a machine with at least 320 megabyte cache, yes, in this case, you can also consider your partition. 512 megabytes. So this is a range. Minimum 128 megabyte, maximum 512 megabyte, right? You have to go through this range. It's better to always go with 128 megabytes. So if you have 2 gigabyte data, how many partition is really suitable? 2 gigabyte. 2 gigabyte divided by 128, right? So guys, how many? I need calculator. So 2 gig. So guys, when we say 2 gigabyte, the data is 128 megabyte. Gigabyte, megabyte, different scale. Firstly, you have to say, okay, 2 is gigabyte, multiply by 1024 to bring it into the megabyte format, and then divide it by 128 megabyte. How many partitions? 16 partition, right? So it means 16 partition is fail. All right. So, okay, now we know that we need 16 partition. You have a machine with let's say with 4 cores, right? But we decided about partition. Now we have to decide about how to distribute this partition across the cores, right? Because of processing. You have 4 cores. How do you distribute 16 partition across 4 cores? I mean, 4 partition per core, right? Because we have to be, it's like a round robin. It's like we have to be fair, for distribution. So we want to discuss, these typical consideration, very important, and these are really important. And once it's coming. If you're invited for interview about, big data, these are typical questions, right? They ask you. And so, okay, and coalesce, I forgot. Coalesce means if you want to increase the partition, you need to work with this syntax, repartition. But if you want to decrease the number of partitions, you need to do coalesce, right? So sometimes we need coalesce. We will discuss, during the term that why we need to decrease the number of partitions, right? Because we always would like to increase number of partitions. Let's go a bit, let's say further. Let's drill it down. Still, we need to discuss on this partitioning. All right. So let's say you have 3 workstations. All right. So and then we usually get first machine or first PC as a driver machine. Right? We get it as a driver because we want to manage the entire cluster, right? Guys, we call it cluster, right? We have 3 workstations. We call it a cluster, Spark cluster, and one machine we call driver, and 2 other machines we call worker, right? Because driver gets tasks from us and is going to distribute it across these worker nodes, right? So it means this is like, some people say it's like client server, saying, okay, this is client, this is server. But yeah, we can accept, right? Because one PC is going to manage the entire cluster, right? But let's use, Spark terminologies, right? Never do client server, right? Client server is for networking purpose. But here, let's use Spark terminologies. Driver to manage the entire cluster, means including these 2 worker nodes, and then these worker nodes means those workstation that they have to go through parallel processing. Okay, your turn. We have 2 cores on each PC and 4 gigabyte memory. So you have 2 gigabyte data. We want to do customer clustering. You want to run a machine learning on a data which is 2 gigabyte. So how do you split how many partition you think is the right choice for this case? So if we go with 16, because we said with 2 gigabyte, if you want to get each data size 128 megabyte, would have to have 16 partitions, right? You can consider it, and then 16 partition, 2 cores means we have totally 4 cores, and then you can, distribute, 4 partitions per core. Or you can do something like this. I said 512 megabytes is also valid. All right. So you can divide them into 4 partitions, guys. Once you divide them in 4 partitions, Spark engine is going to fairly distribute partition. That's the reason. Partition 1 goes directly to PC2, and then partition 2 goes directly to to PC3, and then partition 3, partition 4, right? Because it's going to make sure everything is really fair within this distribution. And then what happened? So once we do this partitioning, right, 2 and 2, why 2 and 2? Why not 3 and? Yeah, this is the point I want to mention many times, because we want to have fair distribution, right? Why? Next question. Why fair distribution? Let's say I want to have 3 partitions. Let's say, okay, ignore this one, ignore partition 4. Let's say you come up with the wrong allocation. It means you want to divide your data to 3 partitions. Partition 1, 2, 3. Okay, let's say this machine comes with only 1 partition, but that machine, PC2, comes with 2 partitions. What is the problem, really? Why we have to avoid it? Why we have to make sure everything is, fairly for this purpose? For the parallel processing. Any? That's perfect. This is perfect. The reason is Spark asks operating system, please give me 2 cores like PC2, because this driver firstly assesses your data and the number of partitions, right? And then this driver asks operating system in PC2, operating system in PC3, asking, okay, can you give me 2 cores because I want to run, the task. I need it for parallel processing. They provide resources to driver, and driver based on those, cores, gonna to decide to distribute this partition. But you do a wrong decision. You want to go with 3. Let's consider where is the problem. The problem is if you divide, as I said, that ignore this one, right? You want to run now your let's say your coding, your action, your method. You want to run your machine learning. So what happened? Parallel processing. It means that at the first run, partition 1 in PC2 and partition 2 in PC3, they get into the execution. Okay, please follow run 1. Run 1 and run 1. Right? It means they get into the execution in parallel. Once they have done, they need to go through second partition, right? So PC2 goes to the second partition, meaning partition 3, but there is no partition. As I said, right? Ignore this one. It means that one core is busy with 1 partition, but you still keep this core idle without doing anything. So guys, this is not really great resource utilization. If you want to run parallel processing, you have to make sure all cores they are busy at the same time to run the parallel processing, right? We need all resources to work together. If one core is going to be idle, doing nothing, so why we have to do this? Because let's imagine on this PC3, you run so many things. This is one task. Let's say maybe on this machine, you have databases, you have IIS server, you have file server, you have email server, you have so many stuff on this machine, PC3. And you deliberately, maybe without the correct, this configuration, you keep one core idle. So in terms of resource utilization, right, it's not good. We have to avoid it, right? We have to avoid it. This is a question that, we usually ask during interview for big data jobs. We ask about underutilization of resources, right? We have to make sure there is nothing happen like this.
Yeah, just wanted to find out if the capacity or the size of the data that you really want to run parallel with is not as big as the core sizes. That means that, for example, you have 4 cores, the smaller yeah, the better. Instead of putting everything just in one.
Okay, very good question. So if you bear with me, I want to go through your question through this slides. Okay, so okay, we found out we need to have, you know, the fair distribution. So take let's say takeaway message on this. Takeaway message on this is if you have on each machine, if you want to come up with 3 cores each, right? 3 cores, 3 cores means totally you have 6 cores, right? Or maybe you want to ask one machine to come with 3 cores, another machine with 2 cores, right? It depends on the availability of cores, right? Let's say if you have 5 cores at the end, the number of partitions, is better to be a coefficient of number of cores. It means that if you have 5 cores, how many partitions? 5, 10, 15, 20, 25, right? Is the coefficient of number of cores. That means you did it with you didn't underutilize, or let's say you didn't take these resources, because you need really, you're not talking about just running one job on one machine or 2 machines, but we're talking about a cluster. Cluster means we have so many stuff running right at the same time. So this is one thing we have to take into consideration. All right. What else? Let's say now we have one PC. Okay. Cluster doesn't mean that we have to have many workstations. You can even do it with one workstation, with my laptop, with your laptop. Also, on this module, we want to go with Google Colab. Are you familiar with Google Colab? Okay, great. So we want to work with Google Colab. We want to install Spark on Google Colab, and then go through Google Colab. So Google Colab, the free version we use, provides us, the minimum resources, right? It provides 2 cores and I think 2 or 4 gigabytes. All right. So guys, so ladies, you know that once you tap it, it's not something because you have to do it within 15 minutes after starting the class. All right. Okay, this case, the same data, 2 gigabytes, the same job, but here you have just one machine. If you have one machine, driver and worker, they are same, right? They are on the same machine. So driver and worker. So in this case, you have 3 cores. How many partitions and what is the size and what do you would like to go with the size of the partition? You have 2 gigabyte data. You have to consider the number of cores. What do you think? So if you have 3 cores, now you have to think like this. I have 3 cores. It means I need to have 3 partitions, 6 partitions, 9 partitions, 12 partitions, 15 partitions, right? So try with the minimum. If you want to have 3 partitions, 2 gigabyte, if you divide 2 gigabyte to 3, what happened? You can try. Calculator. I have 2 gigabytes, right? And then I want to have 3 partitions. Divided by 3, each partition is going to be 667 megabytes. So out of the range, right? It's better to go with 6 partitions, right? It means that 2 gigabytes divided by 6 is going to be 330 megabytes. Now it's within the range, right? So 6 partition is the minimum, and then you can go even with 9 partition, right? You can see how many partition. 2 divided by 9, so each partition 200 megabytes. So, okay, how to decide? Question here, right? 6 partition, 9 partition, 12 partition. They are all feasible, right? So what do you think? What is your idea on this? Because in this case, we find out we can go ahead with 6 partition and 9 partition, right? And also, even with 12 partition, if we go with 12 partition, is also feasible, right? It's 160. So on this scenario, you can have 6, 9, 12. Which one we have to go ahead? So they are feasible. Which one? And what is your reason? 12. 12. Okay, the reason? Okay, good.
In case of machine fails, you lose that one in the small in the power instead of a big source.
Okay, this is also valid. So, you know, guys, the concern is if we have the size of data like 120 megabytes, that's perfect. At the same time, you need to consider how you want to keep your CPU busy. If you have 128 megabytes, you might have, in this case, 12 partitions. But if you increase a bit the data size, and then instead of 12, 12 partitions means 12 tasks. CPU needs to run 12 tasks, right, in parallel, right, 3 by 3, because here we have 3 cores, right? Each partition, at each cycle, we have to run data, 3 by 3. All right, 3 by 3. In this case, I went through 6 partitions. Each partition comes with 340 megabytes. You see that if you have 3 cores, at the first run, core 1, again, core 2, core 3 at the same time. 3 cores going to execute your tasks, your application, your machine learning, whatever, on the first partition, second partition, and third partition, right? I'm talking about 1, 2, 3. The second run, they go through these partition 4, 5, 6. So at the same time, which is another lesson, that at the same time that we want to manage the number of partitions, the size of partition, it's better to do not overuse CPU, right? If you keep your CPU overused, it's going to be still busy with your task. There might be other tasks not related to this spot. As I said, consider a data center, consider a busy machine. They're going to consider like you are working on a machine. At the same time, your machine is busy with the cloud service. Your machine is busy to run, I don't know, on MATLAB, you're going to run something. So your machine is busy with some other stuff. At the same time, you want to use cores and CPU to run this parallel processing. So somehow subjective, right? So it's really subjective. You have to decide based on the availability of resources, right? This is like a trade-off. You need to keep the number of partitions many at the same time. Many, I mean, to keep it minimum 128 megabytes. All right. At the same time, you have to make sure your cores, right, or cores, they are not, overused. Okay. If they are overused, means they are busy with your task, and other requests from operating system, from other applications, they have to wait in a queue, in a buffer, to make sure these cores they get free, and then these cores going to get back to doing application. Right? This is somehow trade-off that we have to consider. All right. Is it clear? That's okay. All right. Perfect. So let's move on. Okay, I discussed about partitioning. Okay, now let's go a bit in data side. Okay, let's say we have this data. So you see, this is like 10 records. Of course, this is not new, but in one of my classes, the student asked me, so you are talking about big data, but why it's not big? I said, sorry, I cannot put like 10 megabyte on the screen. So, maybe you're asking that why 10 records? This is like how I want to deliver the idea of repartitioning, all right? So the idea of repartitioning is, if you have this data, like consider it huge data, before doing, as I said before, doing a processing, we need to partition it, right? How? With this syntax. BF is the name of this data frame, the repartition for. All right, if you say repartition 4, Spark is going to automatically create 4 partitions, P0 to P3. And it's going to divide your data fairly across the partition. That's the reason. You see that size 25%, 25%, 25%, 25%, right? This is the target. What happened? So start reading your data. 1A going to partition 0. 2B go to partition 1. See, right? This is fairly solution. 3C goes to partition 2. 4D goes to partition 3. 5A, keep in the partition 3. 6B, again, start from P0. Guys, repartition, if we see that PySpark randomly distribute. If you run this scenario on your machine, maybe on your machine, 5A is not going to settle in the same P3. Maybe it's going to go in P1. So randomly distributed. But at the end, we are 100% sure there is a fair distribution. All right. So on the case I did, it came up with this partitioning. Partition 0 to 2, we have 3. Within first 3 partitions, we have 2 rows, 2 data, right? And then last partition we have 4. So it seems it's still fairly distributed, right? Because imagine might be, as I said, if you run might be in your Spark running, maybe 10B is going to go over, this one, P2. So it's not a big change, right? So if you just move one data, to partition 0, 1, it's not a big difference, right? Still, we accept it. This is valid. Okay, one more thing. Okay, what I want to say, let me see. Okay, just give me a second. I think I put these slides. Oh, no, I'm going back. So am I wrong? Partitioning. All right, okay, question. Based on the code, right? Have to decide how many partitions based on the code. If you have 3 cores, it means you have to see firstly, consider your data partitioning with 3 partitions. It means first you divide 2 gigabytes by 3.
Oh, yes, I got that part, but I'm saying, why do we go with 6 instead of 12 or 9?
Okay, I said if you want to go 6, 9, 12, these are all valid, right? I've said it's very subjective based on your resources. If your machine, the machine you're working is busy with other tasks, either the Magic Cloud is running, might be, some other services running, it's better to keep core not over, don't overthink it, right? It's better to keep it, like even your machine is powerful, maybe 500 goes out to, one better, right? It's like subjective, what to see, you have to decide accordingly based on, the resources availabilities. Great. All right, so this is really good. We have data, and then you come up, with this partitioning. Where is the concern that usually comes in the interview? So this is exactly the case. We had it in the interview a few months back in venture company, and then we had this question. So we said, all right, we have this data, and we want to partition it on the spot. So what do you think? I'm going to ask, from candidates, what do you think? How we can go ahead? So few students say it's okay. We can use repartition, and then we put them into the partitioning randomly. Okay, we're going to put it randomly. You see that 1A, 2A, 3A, 4A, 5A, and then it's going to distribute it like this. That's perfect. It's fairly distributed, right? And then we asked, the question came up after this, and then we said that, let's say let's say that this data is very huge because if you see the distribution of categories, they are all distributed across all partitions. If you see that cluster A, category A is now in each partition, right? Cluster B, we have just one data, right? It's the C2 partition, D2 partition, right? We said that let's imagine this data is very huge. We have so many, categories. And then we ask, if you have many partitions, right? But if you want to work around only a specific categories, let's say that based on your task, right? You want to work only with category B, right? Based on your task, you want to just work with category A and B, for example, right? So why not to make it, make it, it's best, let's say the best case in this scenario, right? The scenario is you want to work with a specific category, not all categories. So why not to keep, let's say, if you want to work with class A, why not? Ask Spark, okay, Spark, I ask you to divide data into 12 partitions for me. Okay, let's get 6 partitions to just class A, right? What happened? In this case, once we go through parallel processing, just 6 partitions are engaged for, for processing, right? Not all 12 partitions. Okay, you got the point? So the point is we have 12 partitions, let's say. All right, let's say we have 12 partitions, and then let me come here. Let's say you have 12 partitions. You ask, Spark to, okay, I need 12 partitions, but please take A and B into just, let's say, only 6 partitions or 4 partitions. In this case, let's consider 6 partitions. Then what happens? You write a query, you write an application, you write a method, something, then we just want to go through category A. If you write it down, Spark knows that you collected your data category A into only 6 partitions, right? Instead of taking all the partition into consideration for processing, say, all right, 6 partition, we don't need to, more, right? Because you have no category A. We need just 6 partitions that they come up with they come up with category A. So consider that. It's really great utilization of resources, right? Because you, with your own pre-knowledge, you manage this, partitioning. But what happened? This is really good, but the problem happens once you have these categories. What is the problem? Who knows what is the issue with this data? Yes, also in the title I mentioned, right? Skewness. What is a skewness? So skewness means yeah. So, yeah, it means okay, there is a meaning, right? So you can very related, yes, that's perfect. So skewness means there is uneven data distribution, right? Like what we said, right? So uneven data distribution, guys, this is very big issue and concern in parallel processing, right? Why? Let's consider this scenario. We have this data, we have many categories, A, just 1B, 2C, and 2D, right? Sorry? Yeah, it comes with 4 different, right? So, but A is dominating, right? It's getting, 4, 5, records out of 10. So what happened? You said, all right, dear, the syntax, dear Repartition, please do it again in 4 partition. I'm happy with 4 partition, but on category, we didn't mention which one, A or B or C. It's a category, right? It's going to get categories and it's going to get partition. You see that it's going to put B partition 0. Okay, there is one B. It's going to put C partition 0, D partition 2, and A partition 3. So guys, you see that 10% just one data, 50%. What happened here? Who knows what is the concern here? We have one partition more data. So imagine, let me get back to this. Imagine all partitions are 340 megabytes, right? And this partition counts 1 gigabyte. So the rest, they are all okay, but problems with this partition, right? It comes with 1 gigabyte. So if a partition comes with 1 gigabyte, you know that 1 gigabyte means your machine crash, right? Even small crash. Even small is not able to handle 1 gigabyte data in one partition, right? Because maximum size we said is better to be 512 megabyte, not 1 gigabyte. Even if it's 512, again, this discussion is very subjective based on the resources. Even if it's 512 and the rest 340, you say, okay, the cluster worked very well. We have no any concern. Yes, in this cluster, your cluster works, there is no concern. Problem is time complexity, right? We would like to run this. We would like to run this, these, let's say, these power processing to make sure we can do it in 2 minutes, 3 minutes, 5 minutes. The processing, not in 3 hours, 4 hours, 5 hours, right? This is, once you start working with power processing, these are like your observation, you found them out, right? So this is what we have to consider. You might ask me, okay, data skewness, how we can find it? Do we have skewness or we don't? So this is another topic, data skewness, but might be, you can consider this skewness, keep it on your mind. Skewness is the topic that we needed to consider it in every single big data processing, right? So maybe you can take it as your presentation, maybe you can take it as your own study, right? To see how we can handle data skewness to make sure we don't underutilize resources, right? This is the concept. So, okay, one solution to avoid the skewness is this syntax, repartition by range, right? So repartition by range is going to say, all right, still keep, into 4 partitions, still 4 partition or concept, still on the category, but please make a range. Once you say make a range, it's going to keep each partition in the same range. Same range means same size, basically, right? It's not about same size. That's the reason. The problem was with A. Okay, we had no concern with B. We had no concern with C and D. The concern was with A. That's the reason. If you say partition by range, it's going to divide your category A over 2 partitions. You see that partition 0, partition 1. And it's going to, before we had D and C separately, and now they are together. Put them together, right? Just try to manage this skewness. Okay, it's easy, right? There is a solution, it's easy, but still this one is not optimized solution, right? This is just basic mathematics behind that. It's going to do it for us, but very valid solution. All right, guys, these are, what you need to really consider. So you might ask me why you go through this, these tips, because you might get them after 1-2 years, right? Might be. But I wanted to give you, these are the concerns, right? Because usually you should ask me, okay, what happened in industry? What happened in the company? What happened in your project? These are really what happened, right? You need to have your mindset on big data processing, considering these stuff, right? You need to consider these stuff. Okay, let's go through a few questions together. You have a cluster with 5 worker nodes. Here we have 5 worker nodes, and each node has 4 cores, the green one, right? How many partitions would you ideally create for optimal parallelism? Okay, your turn, based on the discussion we had.
Does it depend on how many big parts of work are there or what?
No, we just consider the part of it.
Right.
Okay. Okay, try it, give your thought.
It's depending on the number of data you have.
Okay, 5 worker nodes, 4 cube, and 4 code, right? It means we can have at least 20 partitions, right, minimum. But we said we have a range of sizes, 128 megabyte to 512 megabyte, right? With that consideration, what we can do, okay, this is one consideration. The second consideration, because the purpose of this task is usually in the Spark documentation, right? It says that the optimal number of I think it didn't say optimal, it said the best combination. Okay, let's say the best combination. Say it's the best combination, or let's consider optimal. For the optimal, right? The optimal number of partitions per core is better to take it 2 to 4 partitions. It says for each core, please don't go beyond 4 partitions because of underutilization of resources. It says it's better, right? It's a suggestion. It says the Spark engine works in the best position, in the best case that if we come up with these considerations, minimum 2, maximum 4 partitions, right? For each core. So what does it mean? It means we have to come with this one. So as I said that, it says better to go with 2 to 4 partitions per core. So it means that if we have 5 nodes multiplied by 40, it means we have 24, right? With this assumption, we can provide 2 partition minimum and maximum 4 partition. It means, okay, you can divide your data minimum 40, maximum 80. All right. But you might ask me, okay, if you come up with 100 terabytes, if you come up with 100 terabytes, and then 80 partition is not enough. You see that I calculated, I said, if you come up with, we said minimum is 40 partition, right? Minimum 40 partition, we said the minimum size is 128 megabyte. It means if you have minimum 5 gigabyte data, all right. And if you have maximum 10 gigabyte data, if you want to go with 128 megabyte as a default size, or if you want to go with 512 megabyte for each partition, minimum 40 partition, maximum 80, guys, it means that in this case, the minimum partition is the minimum data size is 5 gig, the maximum data size is 40 gig. So sometimes you don't need to know about the data. You just need to know about resources. And based on the resources, you can calculate how much data you can manage in parallel. In this case, with all this stuff, right? If you have data between 5 gigabyte to 40 gigabyte, is perfect, right? Perfectly work for these cases studies. If you go a bit beyond 40K, if you turn 40K to 40 gigabyte to 60 gigabyte to 80 gigabyte, right? You can still go through this formulation, right? But the problem is, as I said, time complexity, right? It's gonna do, let's say, if your machine, let's say your data center or where you're working, right? Let's say if they consider time complexity, they want to process everything quickly. Let's say these big companies like this Google Cloud or let's say Amazon, we all do good service, right? We never face the availability issues, right? Because they have this kind of formulation, they want to make sure they have well enough resources available for for customers. So this is this is like a minimum standard, right? This is the minimum standard that you have to come up with 5 gigabyte to 40 gigabyte. All right. This is the reason I went through this one to let you know. Sometimes you don't need to know about the size of data, right? If you just know about resources, that's enough, right? You can calculate the minimum and maximum expectations. All right, so next one. So what do you think? So 8, right? If you increase the number of partitions in a PySpark data from 10 to 50, so because it's been found out 10 is the base, right? Based on those calculations, we need minimum 128 megabyte and maximum 512 megabyte. Let's say based on those minimum standards, you find out 2 is a good choice, but you want to say, okay, I want to increase 10 to 50. So there is no error, right? It doesn't mean Spark complete error says no, you can't do that. You have to go with 10, right? So never happen, right? This is how you use your resources. If you go with 50, it means you increase the number of partitions, right? So if you increase number of partitions, it means each partition, the size of each partition, right? Get decreased, right? If it's get decreased, it means memory usage get decreased because at every cycle or at every echo, right? Means once you run your algorithm, your method, whatever, it's going to bring data, right, based on the size, right? It says it's not going to bring all data in one go, right? Because we have just, let's say 10 partitions, or in this case 50 partitions. Okay, guys, the problem, the first part is good. You reduce, the overhead of memory, but at the same time, you increase CPU scheduling over there. Because I've said that if you have 50 partitions, you instruct CPU 50 times. So the CPU do this, CPU do this, CPU do this, or do this, or do this, all right? You increase. That's the reason that this is always trade-off, right? If you increase one side, other sides get decreased, right? And vice versa. Okay, so let's go with another one. Okay, you have 8 cores. All right, 8 cores. They are available for your purpose, right? But you go with 2 partitions. What happened? 2 partition means, in the best scenario, you give 1 partition to each core, right? Core 1, partition 1, core 2, partition 2, right? This is, the best case. What about other 6 cores? This is what it is, right? See, only 2 cores are utilized under utilization. This is a big concept in power processing. I think, okay, but this question is in not really good formulation. So data frame has 4 partitions, but 1 partition contains 80% of data. So yeah, of course, right? Data skewness, right? Agree? Yeah. Data skewness. Okay, how can you fix skewed data in partitions when processing a large data frame? Which one? B, perfect, right? We discussed. If you face a skewness, we need to go with B, right? Repartition by range. So guys, repartition by range, repartition, these are all in your tutorial, right? I recorded video. You just need to go through it. I want to also go through tutorial, right? Don't worry. Just let's go through these concepts. Okay, last one. So, right? So, you can go ahead with, the baseline means minimum 2, maximum 4 partitions, right? It means if you have 10 worker nodes, each with 8 cores, it means now we have 80 cores, right? 80. Consider minimum 2 partitions per core. It's going to be 160 cores minimum, and 320 maximum. All right. Okay, minimum. Let me write it down here.
So you know why I'm proposing this? Because this is what I faced like before, right? That was the reason I tried to share here with you to just discuss a simple tip here. So we said we have 80 cores now, right? So the minimum partitions 160 multiplied by 2, right? Maximum partition 300, right? So all right. And then what you need to calculate, because still 200 gigabyte is there, right? We have to make sure is 200 gigabyte data idle and good enough, with this number of partitions. How we can make sure is it good enough? We need to do calculation, right? Means that you need to multiply this one to minimum 128 megabyte, maximum 512, right? At the same time, do for this one. Let me try here. All right, so I went through 320 multiplied by 512. So this is, 163K, right? I mean, the scale is megabyte, right? Because these are all megabyte. 512 is a megabyte. It means that the best case is to this combination, right? Maximum 320 partitions. The best case is to handle this size of data. But guys, your data is more than this. Again, no worries. You can increase, right? But in the interview, you say, okay, don't worry, we can increase the number of partitions, right? This is not the valid, answer to this question. What we have to do, we have to increase the number of partitions, right? With the consideration of the size. So it means that if we go with this, with 80 cores using 54 partitions, we have this one, right? 160 to 220, 320. But this is not the right decision because they are less than 200 gigabyte data. This is what we have to go through. So I firstly go through, mathematics and calculation, this one. If I find it's not good enough for my data, for my purpose, I try to come with this. Okay, I want to say, all right, partition size, 128 megabyte is the base, 256 middle, 512 megabyte is the maximum. This is the range we would like to go through, right? And then 625 megabyte. I want to let you know why 625 megabyte. And then I go through that calculation. The data I had was 200 gigabyte, right? 200 gigabyte, the second attribute formula, 200 gigabyte. Multiplied by 1024. What is this 1024? Again, changing, right? Because 128 is the megabyte. You need to keep everything in the megabyte, right? So that's the reason we need to multiply 200 by 100, with 1024 means gigabyte to megabyte. In this case, you have 1600 partition if you want to go ahead with that partition size, 128. If you say, all right, 256 megabyte, if you want to consider this, the same formula, 800 partition, if you go with 500, you see that, 400 partition, guys, 320 partition that we found it out based on, more calculation. If you want to go with this one, it means each partition gets more than 500 per megabyte. So let's say in the best case, Spark that doesn't crash, but keep your processing going, and you have to leave out on quickly, right? You have to stop manually. Again, what is the solution here? Let's just start with this one. 1600 partition is idle if there is no shuffle overhead. We will discuss also about shuffling. Shuffling means that if you have, 1600 partitions. If you want to write a join query that needs to go through all partitions, right, and then shuffle all data, it says if there is no shuffling, that this is really good tip. If there is no shuffling, means if there is no join, right? Join is very, let's say, costly operation, right? Join means that you want to join, some database on the relationship, right? This is very common issue on big data. It's better. We can't avoid it. We can't avoid shuffling. At least we can manage it, right? This is how we can manage. If there is no shuffling, it's better to go with this one. The idle one. 800 partition is the better choice because each partition comes with 256. If you go with 400 partition, is a borderline acceptable, right? I've said 500 square somehow is risky to take it over, but first one 625 is too large, right? We can't take it over. If you come up with something like this, you need to decide about your cluster. You have to have this approach. You have to have this mindset, okay? To see, okay, how I'm able to divide data across, machines and code. All right.